Alright, in this video, we're going to be talking about literal equations and how to solve them. But before we get into how to solve them, let's talk about what literal equations mean. So before we even talk about what literal equations mean, let's even take it simpler. What does the word literal mean? In order to do that, we're going to look at some different scenarios. So for this, what's the difference between the following two sentences? It's raining cats and dogs. It's literally raining cats and dogs. Hopefully you're thinking it's raining cats and dogs means it's raining really hard. It's a figure of speech. It's literally raining cats and dogs. That literally means there are cats and dogs falling from the sky, which won't happen. Excuse me. Let's look at a couple other examples. People say, I got your back all the time. Like, I got your back. I literally got your back. That means you have that person's spine. So, not the same thing. So, that word literal means actual or without exaggeration. The definition of a literal equation is a formula or equation that involves several variables. So you might be thinking, so how does that tie into it being literal, or how would we solve that? Well, the answer to that is, when you solve a literal equation, you're using inverse operations to rearrange the equation to isolate a certain variable. Let's break that down just a little bit. So using inverse operations, that should be similar, or that should sound similar to how we solve multi-step equations, because that is the same thing. To rearrange the equation, so that's what we do when we're solving multi-step. We are rearranging to isolate a certain variable. Now, normally in our multi-step equations, there is one variable. We solve for that one variable, we get an answer. If the literal equation has more than one variable, we are solving for just one variable in the same way we would solve a multi-step, and we will still have other variables in the equation. So it's a little weird. So we do actually solve the equation, or literally solve the equation, just like a multi-step equation. We just pretend the other variables are numbers we don't know. So this would be an example of a literal equation. And I could solve this for x, I could solve this for y, it wouldn't matter. But because these are both variables, and we know that variables take place of some number we don't know, but we eventually find. In this case, we may not always find the answer, but there are infinitely many, solutions that would work for this equation. All of these different things would work. All of these different expressions would work in place of x and y. And these aren't even all of them. They could have kept going. There are more. These are just good examples. So now let's actually get into solving these. So I've typed up some helpful hints. I'll read them. You read them as well. And just keep referring back to these. That way, if you get stuck, you have something to go by. So circle the variable you want to solve for, always. That will help you remember what you're solving for. Keep that in mind, and don't put that with something else. You'll keep that isolated. Or remember to solve for that variable. Think backwards, so do your PEMDAS or GEM. So just like we would solve a multi-step equation, you're still doing that order of operation type thing, but trying to get everything away from it. Remove fractions by multiplying the denominator and then dividing the numerator. I know in a previous video we talked about this. This is taking one fraction and getting rid of it by doing two different steps, but you can just do one step, which is multiplying by the reciprocal or multiplying by the fraction flipped. So you can do this, what this says, or you can multiply by the reciprocal, and we'll get into some examples like that. And then the last step is usually. This usually doesn't mean always. It means usually this is what happens, but it could change. So divide by whatever is next to your variable. And then if you're stuck, rewrite the equation with numbers in place of variables. So what I've done is I've found equations that are very similar to these literal equations, or set up similarly. In one example, we'll be solving for the variable and we'll get a numerical answer, and then in the other example, we'll be solving the literal equation and we won't get a numerical answer. It will look confusing, like we need to do more or we don't know more about the problem, and that's what it's going to end up looking like. So let's get right into this. This first example, we need to solve this equation for x. That means we need to get x completely by itself. So first things first, I'm going to go ahead and circle my variable. So wherever your variable is, that's where you need to circle it. And then in order to solve for x, well, 2 and x are next to one another. The way to undo that, I'm sorry, I skipped a step. If they're next to one another, that's multiplication. And to undo multiplication, we need to divide. And since we're trying to solve for x, I'm just going to divide both sides by 2. Oop, that's way too big. Oops, sorry about that. I thought I had my laptop plugged in. I apparently did not. Okay. Oh, my computer froze. And it's back up. Okay, so when we divide both sides by 2, these two 2's cancel each other out, or when you divide them, they become 1. So 1x equals 10, equals 5. I thought I was typing, or just x equals 5. And we could check this by putting 5 back in. So let me do that. 2 times 5 equals 10. Well, 2 times 5 is 10, so that works. Now, in example 2, it's set up very much the same way. We have some variable times the variable we're trying to isolate equals some other variable. So we can pretend that g and then m are 2 numbers. The only thing with that is we can't actually put numbers in place because we're not solving h for a number answer or a numerical answer. But if we're trying to get h by itself, and it looks very similar to example 1. Well, if g and h are next to one another, they're multiplying. So to get rid of g, or to isolate h, or get h by itself, I would have to divide both sides by g. Now, as you're solving these literal equations, one thing you need to keep in mind is because these are different variables, you cannot combine them, simplify them, condense them, anything like that. If this were a m and this were a m, then you could combine them, divide them, apply operations to them. But these are 2 different variables that cannot be combined. So they have to stay as is. So when we do this, these 2 g's are gone, they cancel, or become 1. So I'm left with h equals m over g. Now, this looks very similar to x equals 10 over 2. The difference is 10 over 2 could be simplified, or we could divide 10 by 2. We can't divide m by g in this case because 1, we don't know what m and g are, and 2, they're not the same variable. So this is actually our final answer. I know it looks super weird, But that is our final answer. We've gotten h by itself, and that was the goal. Now, you can check these literal equations. It's going to look a little weird when you do it. So I'm going to type this in. Just like you would double check your numeric answers, you would put whatever you got back into the original. So it's going to look something like this. G times, now instead of h, I'm going to put m over g, equals m. Oops. Okay, so this is the original problem, but now it has our solve for h equation or expression in place of h. And now we can solve this. So I can say this g and this g, because I'm technically dividing, these will cancel, become 1 when I'm dividing, and then I'll just be left with m equals m. Which, even though I don't know what m is, m will always be m no matter what I put in it. So if I put 5 on this side, 5 has to be on this side as well, if that's what the value of m was. So that does work. Hopefully this is starting to make sense, but we are going to do some more examples together. Right, now we have example 3 is back to our numeric. And we need to, again, solve this for x. Now the numeric won't always be solved for x. You could solve for any variable. I just am choosing x right now. So if I want to get x by itself, the very first thing we would need to do if we were solving this multi-step equation is to get rid of this 5, because I can't get rid of the 2 until I get rid of the 5. So I could do the inverse operation and subtract. So I'd be left with 2x equals 6. And then from here, I could divide both sides by 2. So that x equals 3. And then to check that, I could put 3 back in. 2 times 3 plus 5 equals 11. Order of operations, I would need to multiply first. So 6 plus 5 equals 11. And then I could add those two together, and that would tell me that 11 equals 11. So that does work. Right? Now, looking at example 4, look at the setup of example 3, compare it to the setup of example 4. What you should notice is that, again, it looks very similar. I have some coefficient, well, in this case, it's another variable, in front of x, which is what I'm solving for. I have a constant, but in this case, it's a variable, so it's a variable constant. That's a little weird. And then I have this answer. I don't know what A, B, or C are, and if we did know, then we could solve it for a numerical answer. But in this case, we cannot. We are just going to solve it as if it did have numbers in it. So if we are trying to get x by itself, looking at this example, the first thing we did was get rid of this constant by itself. Well, here I can see that this b is by itself, so I can get rid of that. Which would leave me with ax equals c minus b. Now notice that I still have all of my variables. C and b are not like terms, so I cannot combine them. That I'm going to repeat that, and you'll probably get sick of hearing that from me, but you cannot combine these unless they have the same variable. So just continue to keep that in mind. Well, now, in this step, I divided both sides by 2. Here, I can also divide both sides by, in this case, a. So my final answer would be x equals c minus b all over a. X is by itself, it's isolated, so I can say that we have solved for x. And then just like I did for example 2, I'm going to go ahead and double check this to make sure this works. I'm going to do that by doing the equation again. Oh, actually, I'm going to do this. I know that's not the same equation. It's just easier to duplicate and then change than to add a new, resize it, bring it down, and things like that. Okay, so I'm going to completely get rid of this. Maybe. There we go. It wasn't working at first. I don't know why this is not working today. Backspace. Having issues with my computer today, but this was the original equation, and then instead of x, I'm going to put in what I solved for x, which was c maybe if I can get this to work, minus b all over a. There we go. Right, and then in solving for this, I'm going to deal with these parentheses first. So this a is outside of all of this, so this is really dividing this a and this a, so those will cancel, become 1. So I'd be left with c minus b plus b equals c. And you'll see that a lot of them work out this way. Then we have 2 things we can combine because they have the same variable, and because we have this negative and this positive, our additive inverse comes into play and they cancel, become 0, leaving just c equals c, which is what we wanted. So if we knew what c, b, and a were, we could find the numerical value for x, but we don't in this case. Right? Now 5 and 6 are very similar, they have two variables. So in this case, we'll have some numbers in it, but it won't be a numerical answer that we're going to get, right? And these are very similar to the last two examples we just did. The only difference is, instead of this constant being by itself, it now has a variable attached to it. So let's see. For example 5, to get x by itself, what is the first step? Well, it's not asking, do you circle it? It's not talking about that. It's saying, what actually do you do to start getting x by itself? So think about this for a second. Pause the video and think, what would you need to do to get x by itself? What would be the first thing? I'm hoping that you were thinking it's something to do with this term, just like these two examples. You may have been confused on how exactly to go about that, and that's okay. I'm going to show you. So first, I do want to answer the question. Move 6y. That would be the answer. In order to move that 6y though, so we're going to think about the term 6y as just that, a term, something that I need to get away from x. I don't need to do anything to y, so I shouldn't be dividing by -6 because I'm not trying to separate those two. I need to get rid of this entire thing, this entire term. So to get rid of the entire term, I'm just going to move it. The only way to move it to the other side is to do the inverse operation, and that's by adding it. So I'm going to retype this equation down here. Oops, that should be minus. So if we add 6y on both sides, what happens here is that these two become 0. Here, when we add 17 and 6y, 17 does not have a y, so we cannot combine those two. They are not like terms. So when we add 6y to the other side, we are doing just that, adding it to the other side, and it stays over there. It doesn't combine with anything. So 3x equals 17 plus 6y. We literally moved it to the other side. Normally when we move things, they combine, but that's also because they are the same type of term. These were both constants. Doesn't have to be the same constant, but these are both variables, but they're not the same variable. That's why they couldn't be combined. Right? Now, what do you think the next step would be? We're still trying to get x by itself, and right now the only thing next to x is this 3. So that means 3 and x are multiplying, so to get rid of that, or to undo that, we're going to divide. So x equals 17 plus 6y all divided by 3. Now, you can leave this as your answer, and that would be definitely fine. I know in one of the last videos I talked about there was a way to like separate fractions, and I didn't want to get into that then. I am going to say that now, just because you could have a different answer than maybe someone you're working with or a friend, just to show you that it still works. So when you separate fractions, you have to think about kind of what you do when you add fractions. So let's just side note for a second. If I have two fractions that have the same denominator, let's say I have 4 thirds and 5 thirds. I'm just making things up right now. Actually, let's not do 5. Let's do 4 again. I didn't want it to work out completely, that's why I changed the answer. Well, when you have two fractions with the same denominator, you can combine your numerators and have, it would just be one denominator since they are the exact same, and then you could actually do the math needed in your numerator over your denominator. So now we want to take this step. This is where we are, 17 plus 6y over 3. So this step right here and this looks kind of similar because I have two different numbers or terms being added together all over the same denominator, and I want to get it back to this. Well, I can do that by saying each numerator over the denominator. So I can say this is the same thing as 17 over 3 plus 6y over 3. Now, you may be wondering, why would I want to do this when I could just leave it? Which is fine. The only reason I'm showing this to you is if a different answer pops up and you need to know how did they get that answer, or even if you want it to look a little simpler. This would be a way to do that. So now I could think about, or in my calculator, calculate this and see, can I simplify this or reduce this? And 17 and 3 are both prime numbers. They don't have other factors besides 1. So this fraction cannot be simplified. But 6 divided by 3 is 2. So I can simplify this to be just 2y. So if you wanted to, you could say that x equals 17 over 3 plus 2y instead of 17 plus 6y over 3. But both are still correct answers. And I'm going to show you why that is. So let's go back for a second. So I'm going to go ahead and write out the other answer we found. X equals 17 over 3 plus 2y. So both of these are correct answers. And I'm going to start one of the double checks. I might need to do the second double check on the other side. This looks more like a 11, so let me extend that. Okay. Hopefully this will let me do this. I lost my mouse there for a second. Oh no. I was afraid of that. I'm sorry, my computer is doing such weird things. Let's try this again. I may just have to type over everything I need. 3 times x and x is 17 plus, I knew that was going to happen, plus 6y over 3 minus 6y equals 17. Uh-oh, what happened? Okay, there we go. Right, just like in the other equations, these 3's divide out to become 1, and we're left with 17 plus 6y minus 6y equals 17. And then we have these like terms that we can combine. When we combine those like terms, they become 0, and we're left with 17 equals 17. Now I'm going to try the other example, this bottom one, 17 over 3 plus 2y, and it's going to look a little different. But we should still get the same answer. So let me fix this first. Still on the outside, but then we have different things here. 17 over 3. Plus 6y over 3. I'm sorry, we changed that to 2, I forgot. Hoping that this works when I actually type it in this time. Yes, okay. Well, now, in this case, it's a little different because we have two things that are not together in one fraction, so we can't just take this 3 and this 3 and divide them out. In this case, we actually have to distribute, which let me say that we could have taken this 3 and distributed it here, but then had to divide everything by 3 by separating the fraction. So it becomes a little complex at that point, which is why I've been showing you this way. But in this method, when we multiply this 3 to both of these, then because we're multiplying this 3 directly to this fraction, these 3's become 1, leaving just 17. When we multiply 3 to 2y, we get plus 6y, and then minus 6y equals 17. And what you should notice is that this is exactly the same as this, so we will end up with the same answer. Okay. Now that we've gone through a problem with two variables where we're only solving for one, and they both have coefficients, now you should be able to answer to get y by itself in this same equation. What would be the first step? Your answer should be to move the 3x. So we can't move 6y because we have to get y by itself. So that wouldn't help us get y by itself. Okay? So now, let me again rewrite this equation down here. So if we're moving 3x as the first step, are we adding or are we subtracting? Hopefully you said subtracting because this is positive, which means there's an invisible plus in front. So to do the inverse, we would subtract. Just like in the previous example, when we added 6y to 17 and we couldn't combine them, we can't combine them in this step either because 17 does not have an x. So here we will just have negative 6y equals 17 minus 3x. Okay? Just like in the previous example when we divided everything by 3, now we will be dividing everything by negative 6. I was very crooked, my apologies. Okay. And I'm going to write it how it's shown first, and then I'm going to change things about it. So how it's shown is y equals 17 minus 3x all over negative 6. Now, I will say that there's nothing necessarily wrong with this, but I will say you won't see answers that have negatives in the denominator. It's just not something you will see. So I'm going to show you what you will see and how they got that answer, or will get answers like that. So because you don't see negatives out in front, what they usually do is take that negative and kind of multiply that negative to everything in the numerator so that it changes the problem a little bit, but that negative comes into place, for lack of better terms. So when we do that, if I'm multiplying everything in our numerator by a negative 1, so I'm not going to multiply it by the whole negative 6. I want the 6 to stay down there, but I'm just going to multiply everything by negative 1. Let me show that in a different color. And right now, what I'm doing is perfectly fine because I'm doing whatever to both the numerator and the denominator. And negative 1 over negative 1 is 1. So really, I'm multiplying both sides by a version of 1. So this is okay to do. That was supposed to be parentheses around the whole thing. But when we multiply this numerator by negative 1, well, 17 becomes negative 17. And negative 3x becomes positive 3x. And then the 6 in the bottom is now positive. So we went from 17 minus 3x over negative 6 to negative 17 plus 3x over 6. You will see it written more like this than with the negative in the denominator. One other thing you could do, and this is just again for preference, if you like the variable first, you could rewrite it. So I have 3x minus 17 all over 6. So in this case, I'm using the commutative property because the order here doesn't really matter. As long as the operation or the sign in front stays the same, 3x is still positive here and here, 17 is still negative here and here, so the order there does not really matter. So either one of these answers is fine. I'm not going to separate it. You could, and you would just kind of end up with like this reversed, 2x minus 17 over 6 or negative 17 over 6 plus 2x, and it would still work out the same way. I'm not going to do that for this example because I've already changed this so much. Maybe for another one. So last step, double check it. Here we go. So I need to take out this y. Oops, just the y. And put in negative 17 Eek, I did not mean to do that. I'm trying to avoid pressing certain buttons so it doesn't mess up my notebook, but it's still messing up, so. Plus 3x all over 6. Okay. And then you see it looks very similar to this one, it's just the placement has moved and some of the numbers are changed. Well, now I have this 6 and this 6, and I can divide those two to become 1. However, this is still subtracting on the outside, so when I cancel those 6's or they become 1, I'm left with 3x minus negative 17 plus 3x equals 17. So then in this case, I need to distribute this negative to both negative 17 and positive 3x, so that we get 3x plus 17. Two negatives always make a positive, remember that. And then negative times 3x would be negative 3x equals 17. Now I didn't say one thing, I'm sure I've said this before, but just to double check, there's an invisible 1 right here, so that's how we know it's negative 1 we're multiplying everything to. And then we have a set of like terms we can combine, this 3x and negative 3x. When we combine those, we get 0, leaving just 17 equals 17. So this worked. Moving right along, now these two are very similar to the last two we just did, except now these have no numbers at all whatsoever. So if needed, go back, take a second and look. Here I'm solving the literal equation for C. So the first thing, so this is similar to 6, the example we just did, because it's in the second term. What we're solving for or trying to get rid of. So if I need to get C by itself, what do you think we should do first? Hopefully you were thinking get rid of the term AB, and it's positive, so we need to subtract on both sides. So we're left with CD equals G minus AB. Now again, just like all of the other examples, G and AB are not like terms, so we cannot combine those two. If we're trying to get C by itself and CD are next to one another, I can get rid of D by dividing everything by D, which would leave C equals G minus AB all over D. I just realized I stopped boxing in some of the answers. Right, and then to check this, again, put it back in. Oops. I'm going to actually use this one, because this will be almost similar. And I have to change all of the variables. Taking the last example and changing it, this now becomes AB this is plus C, I'm sorry, that's what we're trying to solve for. So this is a little different. So now we're going to have C, which equals, oops, here we go, G minus AB all over D times D equals G. And then in this example, this D is being multiplied to this entire fraction, so these D's become 1, and we're left with AB plus G minus AB equals G. We have like terms we can combine. Oops, that was supposed to circle the negative as well. I don't know why that circle was so big. When we combine those two, we get G equals G, which is what we wanted. So that works. I didn't say this before, but for the last one on this problem, take a second, pause the video, see if you can do number 8 without my guidance. And of course, I will be working through this as well. So for this one, if we're solving for A, we need to get rid of B, get rid of C, get rid of D. The only way to, or the first thing to do would be to get rid of CD by moving it to the other side. My handwriting on my computer is just not good today. My apologies. So we'd have AB equals G minus AB. And just like all of the other examples, G and AB are not like terms. I'm sorry, this was supposed to be CD. I don't know why I put AB. G and CD aren't like terms. My apologies. So they cannot be combined. And now I can divide everything by A. I'm sorry, I'm solving for A. I'm thinking way too much. Or divide both sides by B. So B equals G minus CD all over B. All over, this was supposed to be A, I'm sorry. I was like, it's not supposed to equal B. I messed up in that. So A equals G minus CD all over B. My apologies for that confusion. And then double check it. Okay, so here, this needs to be A is what we solve for. Let's do this. So A was G minus okay. there we go, G minus CD all over B times B plus CD equals G. There we go. So I put this back in for A. And then, oops, wrong thing. Because this B is being multiplied to this entire fraction, these B's cancel, become 1, where they divide and become 1. And then we're left with G minus CD plus CD equals G. We have like terms that we can combine. I never boxed this in. And then once we combine those like terms, we end up with G equals G. Okay. So we have now gone through all 8 of the example ones we would have done together in class. I'm going to go over a few more on the next page, but not all of them. So the answer key is posted and you may look at those. So we're going to start off with number 2, mainly because there are 2 ways to go about this, and one way looks a little bit more complex than the other. So if we're solving for t, we need to get rid of everything else, but because p and r are connected to t, we can't do that first. We have to get rid of this p first. It's positive, so I can move it to the other side by subtracting. So a minus p equals p RT. Now, if we're trying to get t by itself, and p and r are right next to it, what are p, r, and t all doing to one another? Hopefully you're thinking they're all multiplying since they're all right next to each other, which is true. That means we can divide them at the same time. So if I want to get rid of p and r, since p and r and t are all multiplying, I can divide p and r at the same time. So t, let me write this down here, equals a minus p all over pr. So that may have looked a little complex, but it became not so complex. Let's erase this. Okay. Before I go ahead and check this, I'm just going to go ahead and talk about the other way to do this. Now, this is a little bit more advanced for right now. Later, when we talk about factoring, which won't be until much later, but this may come back, or we may bring this back and it'll make a little bit more sense. But I'll show it. You may have also seen this before, which then it wouldn't be new. So because these both have a p, think about when you distribute. When you distribute something, it goes to both or whatever is inside. So you end up with, let's say if I had an x on the outside, I would have fx minus 32x. So they would both have an x. In this case, these both have a p. So what I'm going to do is kind of undo that distribution that may have occurred to have both of these p's so that I change the problem completely. And now that p is on the outside. Well, when I do that, I have to think about what it would have been originally. And here, because instead of multiplying, I'm kind of dividing both of these by p to get it back on the outside. If I divide p by p, well, that's just 1. And if I divide this PRT by p, all that's left is just RT. So it changes it a little bit. It is still the same problem, even though we've changed it a little bit. Now our answer is going to look a little different because I'm not going to simplify it to its simplest form, even though that's normally what you're supposed to do, but you'll see why I'm not going to do that here in a second. So now, if I want to get t by itself, it's connected to r, 1 is being added to it, but it's inside of these parentheses. So before I do anything, I have to get rid of this p. So I'm going to divide both sides by p. So that leaves a over p equals 1 plus RT. Now I can get rid of this 1 by subtracting. However, when I do this, I need to make sure I'm subtracting it to this entire fraction. So I'm going to rewrite this like a over p and put minus 1 next to it. That way this entire fraction is being subtracted by 1. And then the last step would be to get rid of r. So I would need to do that by dividing. So when I do that, I'm left with this weird fraction. Now normally we would not want fractions inside of fractions, but that's a little bit advanced. So I'm going to leave this as is and just say that another way to write this is a minus p, or I'm sorry, a divided by p minus 1, that whole fraction minus 1, all over r. Now, in simplest version, it would be this. A minus p all over p times r. This is supposed to be a p. But this is another way to write the answer as well. Now let's move on to the checkpoint. Second one. So a equals, whoa, what happened? There we go. Okay, a equals p plus pr and then t equals a minus p all over pr. Okay, so in this example, or in this double check, This PR is being multiplied to this entire fraction, where PR is also the denominator. So I can divide both of those to become 1. And then we're left with A equals P plus A minus P. I have like terms, so I can go ahead and combine those. And I'm left with A equals A, which is what we wanted. There we go. And now I'm going to go ahead and do the second double check with this version. It's going to look a little different. I need to change this up a little bit. So I have to format this a little weird. So that it works. I knew that was going to happen. Alright, give me a second so I can fix that. Alright, so what's going to happen in this case is going to be kind of similar to what we've been doing, but there'll also be different steps. So here, even though I'm multiplying P and R to this whole fraction and there's not a P and a R down here, there is a R. So remember that even though they're together, they can still be separated. So I can divide this R and this R, which would leave, let's see if I can just type it or just write it. A equals P plus P times the fraction A over P minus 1. That was supposed to be a 1. It looks more like a B. Let's try that again. Right? Now, because there is a P here, but there's not a P underneath the 1, I need to distribute this P to both of these. And when we distribute this P to this first, I can divide this P and this P. So I can type at this point, A equals P plus this P and this P divide to become 1, so all that's left is just A. And then when I multiply this P times -1, I get negative P. So even though it looks very different, we end up with the same thing we ended up with up here, so we're going to end up with the same answer. Right? We're going to do number 3. Now we need to solve for F. F, again, like we were talking about with the second example, is inside the parentheses. So in order to get rid of, or get f by itself, we need to do everything, or get rid of everything outside of the parentheses first. So if you think back to the rules, when it was talking about the fraction, this is an example that this applies to. So in order to get rid of this fraction, you can do one of two things. You can either multiply everything by 5 and then, multiply everything by 9, so both sides by 9, and then divide both sides by 5. So 2 different steps. Or instead, you can multiply this entire side by the reciprocal of this, which would be doing those 2 steps in one. That was supposed to be a 5. It looks more like a 3. And then do the same thing to the other side. Remember, what you do to one side, you have to do to the other. So when you do that, this 9/5 and this 5/9, they are inverses of each other, and that multiplicative inverse becomes just 1. So here we have 9/5 C equals F minus 32. And then the last step to solve for f completely is to add 32 to both sides. This formula may look a little familiar because this is how you convert Celsius to Fahrenheit degrees, and vice versa. Right, so here, because this has a C and this does not, those cannot be combined. They are not like terms. So 9/5 C plus 32 equals F. And then to double check that, I'm going to put this equation in for F. Right, so it took me a second to get that, but here I have put in brackets the equation from F. Even though I put them in brackets, F wasn't multiplying to anything inside the parentheses, so the only reason I'm using the brackets is to show that I put the equation for F in. Because I really don't need it. Because I really don't need it, I can say that I have like terms right here that I can combine, and they will cancel. And I'm going to duplicate this one more time, so hold on. Okay, so those two 32s cancel, or add and subtract to become 0. And now I'm left with C equals 5/9 times 9/5 C. Well, again, like we saw earlier, that 9/5 and 5/9 cancel to become 1, so we're just left with C equals C. Right? Moving on. For number 5, we have to solve this for B. Notice where B is, and your first thought may be get rid of the C, which wouldn't be invalid. That just wouldn't be the first thing you can do, because we can't get rid of the C because everything is being divided by D. So in order to solve this, you have to get rid of D first. So I'm not going to solve this one completely. I'm just going to put that as a first step and say that after you multiply both sides by D, you would end up with DA or AD, it does not matter the order there, equals b plus c. From there, you should be able to solve for b, and you should also be able to double check at this point. Again, if you need help, the answers are posted and you can come back and look at those, or we may talk about that in one of the lessons. For number 6, we need to solve for b1. So these, oh, that was a terrible circle. These small numbers don't really mean much. They're just another way to number or name a letter, especially because they don't want you to combine them. So instead of saying like X and Y, they wanted to use B for both, but they just called this one B1 and B2. So just another way to name it. So this is going to be kind of similar to the problems we were just doing. I want to get B1 by itself, but B1 is inside these parentheses, so I need to get rid of this 1/2 and this H before I do anything else. Now, 1/2 and H are being multiplied to this, so you would think to divide, but when you divide fractions, what ends up happening is you end up multiplying by the reciprocal. So I'm going to do this in 2 different steps. I'm going to focus on the 1/2 first and then do the H. So if we can multiply by the reciprocal anyway, I'm just going to go ahead and do that. The reciprocal of 1/2 is 2 over 1, which is just the same thing as 2. So I'm multiplying this side and this side by 2. By 2, and now we're left with 2a equals h times b1 plus b2. And now we're going to go back to what we said earlier. H is being multiplied to this fraction, so to get rid of it, I'm going to multiply this entire fraction by h, and this side by h. So we're left with 2a all over h equals, well, this h and this h, they will divide and become 1. That 1 is not necessary, so I'm just left with b1 plus b2. And since we're solving for b1, I can get rid of b2 by subtracting. So that's going to look like 2a divided by h, and this, wow, that did not look like an h at all. There we go, that's better. And that entire fraction subtracted by b2. Another way to name these or call these is b sub 2, because this is really a subset. B sub 2. So you could say that equals b sub 1. And the last thing we have to do is check this, and then we are almost done with this video. Sorry. Alright, so I went ahead and I put the equation for b1 into where b1 was. And again, I used brackets just to show that equation from b1. They weren't necessary. And again, because they're not necessary, I can see that I have common or like terms. And I can combine those two. I went ahead and combined them already, so I wouldn't have to pause the video again. So when we combine those two, they become 0, and we're left with just a equals 1/2 h times 2a divided by h. Well, in this case, we have two different sets of inverses here. We have 1/2 and 2, so those are going to multiply or divide and become 1. We also have h divided by h, so that will also become 1. So those will become 1 at the same time, and we'll have a equals a, which is what we wanted. So hopefully you have a better understanding after all of this as to how to solve these literal equations. I did say we're almost done with the video, which is true. I just want to go over one more problem. We're going to do one of the word problems, and we're going to do this first one. The perimeter of my living room rug is 57 feet. Now this is not accurate. My living room is not even 57 feet, but let's say it was. The perimeter of my living room is 57 feet. Calculate the width. I forgot that this said perimeter. Now 57 may not be as inaccurate as I thought. Anyway, I digress. We need to first, let's find what's important. And I'm just going to underline instead of highlight because it's on this weird yellow. So we know we're looking for perimeter. And we know the total perimeter is 57 feet. And they want us to find the width. Now, they give us this picture of this rug and they say that the length is 16 feet. And we will look into that and use that here in a bit. But before we do that, we're going to pretend that we didn't see this picture first. And we're going to set this up. So the very first thing we need is the formula or the equation for perimeter, which, if you remember, you add up all the sides, which would be length plus width, or that's the same thing as 2L. I'm going to draw in the L because I don't want it to, actually I'll just make it capital. There we go. Plus 2W. So that is our equation, our formula for perimeter. And now, before we do anything else, because we've been dealing with literal equations and we need to calculate the width, I'm going to say that W is now what we need to solve for. So we are going to solve for W. So in this case, again, I'm going to do this two different ways. So the first way you may be thinking about this is to get rid of this 2L, which is fine. Get rid of the 2L by subtracting on both sides. So we're left with P minus 2L equals 2W. From there, we can solve for W by dividing both sides by 2. So P minus 2L all over 2 equals W. So remember that I said that you could separate your fractions. If you wanted to do that here and say P over 2 minus 2L over 2, well, 2L over 2 is the same thing as 2 divided by 2, so that would just be 1. L. That would be okay as well. So that's just a side note. The other way I was actually going to say is, remember how we were talking about that example with the 2 P's and we like took a P outside? We could do that here as well. We could take these 2 out since there is 1 for each. And when we do that, I'm going to rewrite it up here. We have P equals 2 times, Now if we're dividing both of these by 2, just L and W are left. So then from here to solve for W, we would need to get rid of this 2 first by dividing by 2 on both sides. Now I've already started running out of space, so I'm going to move this here. P over 2 equals L plus W. And to solve this for W, we would need to get rid of L. Now you may be thinking, wait a minute, isn't that what we just got over here, but we did that a different way? You are correct. When you separate your fractions, you end up with the same answer as when you take the 2 out of both of the coefficients of the coefficients. So either way you do this, you're going to end up with one of these two things. Alright, now that we have some equations solved for W, now we can go ahead and put the 16, which we know is L, into one of our equations, and it doesn't matter which one. I'm going to show both to show you that they both work. I also know that the perimeter is 57 feet, so I'm going to be using that as well. So let's do this first one first. I know the perimeter is 57. I know the length is 16. And I want to see what does W equal. So you could put this all in your calculator at once, or you could do -2 times 16, which would be -32. 57 minus 32 is 25. 25 divided by 2 is 12.5. And if we're being accurate, this would be in feet. I'm just going to type this. That would have been a lot faster. Okay. Before we go into the double check, I'm going to go ahead and do this one as well. So this one would be 57 divided by 2 minus 16. (57) divided by 2 is 28.5, and 28.5 minus 16 is still 12.5. So that would have still worked. Right? And then in this very last part of this problem, I know you're like, yes, finally, we're done. We just need to double check. So I'm going to put all the numbers we found into this original equation. P equals 2L plus 2W. So I'm going to write the equation first. P equals 2L plus 2W. I wanted that to be green. And then from there say, well, I know P is 57. I will rearrange this here in a second so that that Smart Notebook limited mode is not on top of these. Equals 2 times, we know our length is 16, plus 2 times, we just found that our width is 12.5. So let's see. 57 equals, well, 2 times 16 is 32. 2 times 12.5, or 12.5, is 25. And 32 plus 25 does, in fact, equal 57. So this is correct. So that concludes this video. Make sure that you look at the other notes and practice, and then if we're doing this in one of the sessions, make sure you pay attention to that as well.